Today we've got synthesis of Benzil, and it seems pretty straightforward where you dump in concentrated nitric acid. The yield on this is always pretty crappy. We'll talk about that again later, so let's just get right to it. The only UV I have on hand is simply what we already looked at, the benzoin, which is your starting material. I think it's pretty obvious that if you make Benzil, you're going to have something similar looking to this. So the purpose of the UV is simply for you guys to get used to more software, and you get used to what the ultraviolet spectrum looks like. Assigning this, you can't say much other than arguably if you have an aromatic ring or any pi bond, you're going to label the most strongest peaks as some type of pi to pi star. That's about all we could say. So the IR, we already looked at this one, and benzoin crude. So we already did this one. We talked about how these two are the OH stretch. They're quite tight because this thing apparently hydrogen bonds quite specifically. You've got, and I better get a pointer, anything just to the left of 3000 is sp2 hybridized carbons with an H on them stretching. Some people call it, aromatic CH stretch. It doesn't really matter because all it takes is an sp2 hybridized carbon with a hydrogen on it to be just to the left of 3000, just to the right 2975, and that's going to be sp3 hybridized carbon with a hydrogen stretching. And in this case, there's only one. There's one H right there that does that. Then you have your strongest absorption, 1678. That's going to be the carbonyl C double bond O stretch. The classic aromatic ring signature is something just like your Pavia book will normally circle 3 sort of peaks and call it aromatic ring, carbon, double bond carbon stretch. If you had a molecule with just carbon double bonds, you'd see stretches here as well. The only other thing I would look at is the mono-substituted pattern. You've got 2 mono-substituted rings, so you might see a little extra duplication. This one, 755, that one, both of those rings have it. So you could arguably circle this and just call it mono-substituted OOP bend of an aromatic ring. I don't have an actual Benzil that we ran on a product. I have a reference one off the internet. So clearly, this one is that structure, right? So clearly you're going to have, you might think you're only going to see one carbonyl, but it turns out that for some reason, we're going to see 2. And I actually wrote in the numbers that our spectrum normally gives for those C double bond O, and there's going to be 2 of them. You can just say it's the carbonyl stretches. For some reason, this likes to take on a specific orientation where the 2 of them are slightly different in frequency. This is the overtone, the spike of the C double bond O overtone, and this one is it is just past 3000. It's the sp2 hybridized carbon with a hydrogen stretching, or you could call it the aromatic CH stretches. We have right at 1600 these 3 aromatic carbon double bond stretches, and then the mono-substituted area. I gotta be a little careful here. This is 650. I don't really like the looks of this one as much. 650 is a bit low because normally the mono one is more like 670, 680 plus the 720-ish. If I was going, and you got 2 of them, so I might circle these right here and call it mono-substituted OOP bend. That's about it for that. We go on to NMR. We have to review the starting material. We did this the other day, but we'll do it again. So we'll start with benzoin starting material, right? The H that I've labeled D is the one at 6. If it's talking to the OH, labeled E, you'll see them each be a doublet. If it's not, you just see 2 humps. So depending on the concentration how you made yours, you'll see it that way. And we talked about this a bit. The integration here is 2 to roughly 8. So normally the two ortho hydrogens next to a carbonyl, those two get pulled further left. So that would leave 1, 2, 3, 4, 5, 6, 7, 8 hydrogens for the rest of the aromatics. You see how that's really close to 8. So you could definitely label this blob roughly to what I've called A. All the rest, you could circle this and just say the rest, or, B, C, F, G, E. That's the proton starting material, your starting material, carbon-13. Obviously, E would be furthest to the left, that little spiky thing. And any of your carbons that have no hydrogens on them, such as D and G, they will be just as short and stubby as E was. So there was your carbonyl at 190 something. You're going to see 2 right there, so that would be what I called D and G. The mid-height ones, if you see a difference in height, the taller ones are either duplicated or overlapping. So positions A and J, there's only one of them. So it turns out that you see 2 peaks at this mid-range height, A and J, and then this is the rest, which would be B, C, H, I. F, of course, is furthest to the left, and it's built right in just to the right of the solvent triplet peak. Whoever made this one, it wasn't very concentrated, so that is the carbon F. Moving on to the product, Benzil. Now, obviously, this looks like it has quite a bit of symmetry. This is the hydrogen one, so the only hydrogens is A, B, and C. Oftentimes, the one that is ortho to here should be furthest to and because it's symmetrical, you'd say this is 2 and this would be 3. So now whoever did this one did not integrate. If it turned out that this blob was 2 hydrogens and this turned out to be 3, then you could say this blob, sort of a forest, could be called A, and then B and C would be this to the right sort of blob. This is normally what it looks like. That's TMS at 0. See how this one's pretty clean? You might see a tiny bit of trace of something, but because it's not obvious what it is, we don't bother. I don't see, and there was no peak over here for benzaldehyde either, but you might see very tiny traces of something else. But for the most part, this is what your product looks like. The C13, you're going to get up to 5 carbon signals. E would be furthest to the left, and that was approximately 196-ish, kind of. Remember how we said D has no hydrogen on it, so it's going to be just as high as E most of the time. So the same height as that one. So that short one has to be D. B and C are duplicated, so it might be that A is mid-height, which is right here. The remaining 2, B and C. I don't know which of these 2 is B and which is C, but you circle them that way. Clearly, at 77, this little triplet, that is the chloroform NMR solvent showing you its peak. So I believe we've nailed that down. Now we move on to discussion. So the mechanism, you don't have to have it because the nitric acid acting on it, oxidizing, it's not a McMurray, it's not a common one that we'd have to know, but if you find one online to suggest, that would be nice. Some observations leading to discussion, we'll get to that, but the energy curve. The one thing that's interesting is this. Since we don't officially know the mechanism, it's interesting to say to yourself, we know that nitric acid is really, really reactive. So in Mother Nature's energy chart, it's way up here, right? Super reactive. Your starting material and final product are closely related, and that's why I'm saying for qualitative purposes, I'm not really going to suggest this one must be higher in energy. If I had to guess, it might be slightly. And then because we don't know the mechanism, how many intermediates may or may not be in this reaction sequence? We don't know, but the point is this. We definitely heated it, right? So what's the deal with that? Is it possible that the reaction is just slow, which normally means we're heating it to speed it up, but overall it could be exo? Or are we heating it because of the endo factor? Does it really need to get way above? There are some reactions that can happen fast. It's endothermic, meaning your final stuff is higher, but room temperature is more than enough to give it the energy it needs, right? So we don't know for sure which way it is, and putting into calorimeter in this case, this is a great example to think about the possibility. It could be the height of some hill could be really high, which makes it slow, which is a kinetic thing. So that's a thing that in industry, if this is an industrial process and you want to make it much more efficient, or even if you want to research the mechanism itself, you'd really have to start studying the mechanism, how many steps are there, and really identify whether it is kinetically slow or is there a thermodynamic reason for heating. So it's a point of interest that could be made. This is a great example to look into it if we wanted to. The color, obviously it's yellow. Now the interesting thing here is we know you're shrinking the pi to pi star. This has 8 pi bonds because both the carbon and the oxygen are sp2 hybridized and they're all in conjugation. There's 8 total. And the comment to that was even your previous number 3, when you start looking at a bunch of compounds, you notice that even your chalcone, which was yellow, 2 phenyl rings, which is 6 pi bonds plus 2 more, right? That gave you yellow. So it's almost like 8 pi bonds in conjugation is, where you really need to start to seeing any kind of visible color in the organic compound. It's just a point of interest. Yield. The yield for this is always crappy, but yeah, don't use the word crappy in your written discussion. And on the same note, don't use personal type first person nouns or whatever you want to call them, my, I, me, we. You can't say that. You don't say our or my reaction did this. You say the reaction developed heat, or the reaction got hot. You don't say my reaction. So anyway, why is the yield always crappy? We really don't honestly know, because you clearly get yellow color, which is your product. You don't see any obvious signs of black or brown, which is normally what decomposition looks like. We know nitric acid is super oxidation capability, so you might think we're losing yield to stuff that's falling apart, but we don't see black or brown. So the question is some of this compound magically and nicely decomposing? So for example, what if hypothetically we were breaking this and liberating CO? I'm just making this up, but think about it. If that happened, the CO would go away and you'd be left with benzene. If that took place, then you could check in the HPLC of your filtrate for any remaining organic stuff. But in this one, it's very important to note that everybody gets a really bad yield, right? So you either get nice yellow looking product or not much at all, and there's no black or brown. So that's an interesting look at the discussion. You guys should get better at doing it yourselves. That's all I got.